Wow. Okay. So I hope you can see me and hear me okay, students. Thank you very much for being here. I really appreciate you being here. I know you've been at school all day and now it's extra school, but we've only got 2 or 3 more lessons before the examination, so I will try to cover as much ground as possible. Probably the most important topic in the examinations is Organic 2. Organic 1 is very important, but Organic 2 always has questions. And I'm going to show you some, and I'm going to be sending your teachers some questions with the answers of organic chemistry questions that have come up in the last 3 years. They have changed the style of the questions, so it is important that you have a go at lots of questions. Okay, here we go. I'm just going to hide all non-video parts. There we are. Okay, so here we go. I hope, Silver Spring, you can get your camera on so we can work together. So I'm going to share a screen. I'm going to tell you about, we're going to make sure you can identify individual molecules, that you can do isomerism, that you can change one chemical into another, and then we will do things like polymerisation and so on, and then we will look at some questions. It's a lot to do. Firstly, how many of you do feel good about identifying, if I showed you a molecule, how many of you do feel that you would be able to recognize what kind of organic molecule it is? If you think you would be able to recognize it, if I drew one, would you be able to recognize it or would you not? What do you think? Every student, come on, St. Mary's, come on, what we need. Would you be able to recognize, not recognize if I drew something behind me? Would you be able to recognize what it is? Some people are saying, yeah, okay, look, let's have a practice. Let's just see, because this is really important. So I'm just going to draw a molecule behind me. Hang on, just going. So here is a chemical. There it is. What is it? What kind of chemical is it? Can you name it? There it is. Don't worry that I have drawn this as OH here, as O and then line H. It's the same as just OH. What is that chemical? What type of chemical is it? And what is its name? Silver Spring, you can not mute yourself and just tell me if you're happy about it. So can everybody recognize that? Okay. I'm not going to ask for all the names and so on, but do you feel happy about being able to I'm going to tell you what it is in a minute. Are you happy about it? Not quite sure, or not happy about it? Tell me. St. Mary's, yes, maybe, no. Okay, yes. Silver Spring, not quite so confident. Oh, yes, confident, good. Wamouini, yes, no, maybe. Okay, that's good. So, does anybody want to switch on their microphone and tell me what that is? Anybody want to tell me? Anybody want to write it and just tell me what that is very quickly? Okay, so let's have some more speed to this. Let's have some more people getting ready to do it. So I'm going to... Okay, well, my full screen is not... Do you not have full screen? If you go for the speaker on yours, it should show it. I should be full screen on yours if you ask it to be. If you pin me, you should make me full screen. Anyway, that there is an alkanol. That one there is propan-2-ol. It is called propan-2-ol. If you thought it was propan-2-ol, that's fantastic. Okay, that's really great that it's propan-2-ol. and that is exactly what it is. The first bit of this is going to be quite easy, I hope. So I'm going to do the presentation now. Usharika, you have to make your own full screen, not me. I'm already on my example. I run 2 computers. I can see myself full screen, so you need to practice doing that yourself. Okay, here we go. So I'm going to share my screen, and hopefully you will be able to see Organic Chemistry 2. Now, Organic Chemistry 2 is all really about making one chemical into another. So what we're going to do is we're going to run through it. We're going to start in a really simple bit of it. Let me just go. Here we are. So we're going to start by recognizing molecules in isomerism. I need to just make sure that everybody can do this really easily. Okay, it is simple, so we're not going to spend much time doing it. Here we are. So you have to know alkanes, alkenes, alkynes. That's all form 3 stuff. And then the alkanols, the alkanoic acids, the esters, polymers, and soaps and detergents. There are a few other bits and pieces, but those are the main chemicals which you have to know about. The first 5 you will get as individual chemicals. So this is it. If we want to try and recognize the molecules, you should know the general formula of each of the boxes. And the best way to think about it is that the first 3 are very similar, and then we have alkanols and alkanoic acids. If you look at the general formulas, if you look at alkenes, the number of hydrogens is twice the number of carbons. Okay, so the number of hydrogens for alkenes, the number of hydrogens is twice the number of carbons. That's easy. For an alkane, it is 2n plus 2. From an alkyne, it's 2n minus 2. So in other words, if I want to have an example of an alkane, if I had 3 carbons, then it would be 2 times 3 plus 2, C3H8. For an alkene, it's just twice as many, C3H6. For an alkyne, C3, 2 times that, 6 minus 2, H4, C3H4. So that allows you to recognize whether something is an alkane, alkene, alkyne. Alkanols are like alkanes, but with an OH instead of one of the hydrogens. And alkanoic acids are the same again, but with COOH on the end. Here are some examples. C5H12, C5H10, C5H8. And then just like the alkane, for the alkanol, just like the alkane, but lose one H and put OH on it. Okay? Lose one H and put OH on it. If you're, St. Mary seemed to find it very difficult to read this, which is a shame. I will try and make it easier in just a minute, but I think if you're watching it on a phone, you have a problem. It's quite small. Alkanoic acids, we're looking at COOH. So OH for alkanols, COOH for alkanoic acids. So I'm going to stop sharing now. I'm going to stop sharing. I'll go through it on the board because I think some people are finding it difficult to see. So here we go. So for alkenes, it's CnH2n for alkenes. Now, for alkanes, so this is the enes. For the anes, it's this plus 2, CnH2n plus 2. For the ines, the alkynes, it is CnH2n minus 2. So those three make it easy. So if we have CN, any molecule, so if I write a molecule, let's have C4H8. If I've got C4H8, I look at the balance between the hydrogens and the carbons. I don't have to draw it out. It may be helpful to draw it out, but I don't have to draw it out. Because I can go, well, if N is 4, this here, the number of hydrogens, is 2N. If it's N2N, then it's this one. So it must be an alkene with a double bond in it. The other way of doing it is drawing it out. So I have this molecule, forget that. I have this molecule and I start to draw it out. 4 carbons. 1, 2, 3, 4. I'm going to join them all with single bonds to start with. Now I'm going to put 8 hydrogens round. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Hydrogens only join onto 1 carbon. 1, 2, 3, 4, 5, 6, 7, 8. And now I look at the carbons. Is there a problem with any of the carbons? This carbon only has 1, 2, 3 bonds. This one only has 3 bonds. It's that. And if it's a double bond, it's an alkene. Really simple, really straightforward. That's what we're looking at. We're looking at either you look at the general formula or you draw it out. That's okay. Alkanols only have an OH on them. So they're exactly the same as an alkane, all single bonds, but then instead of one of the hydrogens, so this would be 4 carbons, butane. So instead of it being butane, I take one of the hydrogens off. It doesn't matter which one. Let's say it's this one. And I put OH on. We often write just OH. We should really write a line, an H. So this is now an alkanol, and it's still 4 carbons, so still bute. So it's butanol. But we have to say that the OH is on the first carbon. Whichever end we count from the end nearest the OH. So this is butan-1-ol. Butan-1-ol. Looks funny to have a number in there, but that's what we write. When we come to the alkanoic acids, we have to be careful that we count things properly. So I'm going to turn this now into an alkanoic acid. And I do it with a double bonded oxygen. Must be double bonded. I have seen some KCSE questions where they have just put a thicker line there. It should be 2 bonds. So this, it is, a lot of people make a mistake with this, and they call this propanoic acid because they go 1, 2, 3 carbons and COOH. Now the COOH is what we call the functional group, but that carbon is part of the chain. So this is butanoic acid, not propanoic acid. Okay, always count that one as part of the chain. Okay, so alkanes, alkenes, alkynes, fairly simple, and then alkanols and alkanoic acids. Now I'm going to just do a little bit on isomerism. Isomers have the same molecular formula. I'm sure you know this, but it's just important to remember it. Same molecular formula and different structure. Now, sometimes people call it the structural formula and sometimes just structure. It's okay. If you wrote just structure, that's okay. The most common isomers that they ask you to draw are for pentane. I don't know why it's difficult, but what you've got to do is remember one thing, that simply bending a molecule does not make it an isomer. So let's have a look at pentane. So pentane, it's an alkane, so it's CnH2n plus 2. So it must be C5H2 times 5, 10, add 2, 12. Now the obvious way to draw it out is 5 in a row. Just for a minute, I'm not going to draw all the hydrogens. I'm just going to say that's it. Because isomerism is about changing the structure of the carbon chain. And just putting a bend in it doesn't make any difference. So watch. This looks a bit different, and it's not. It's exactly the same. It's exactly the same. Oh, you can't see it. Okay, hang on. Let me just see if I can make it a bit better. Just a moment. Is that a bit better? Bit better? I hope that is a bit better. No? No one really? Okay, I will do something different. I will do something different. Hang on. Hang on, I will do something different. I'll see if I can do something different. If that's difficult to see, it's funny because I can see it, but that doesn't matter. Let me just move back to this. Hang on. Let's just try. I hope you can see that. Can we all see that okay? Cool. Okay. So I'm not drawing the hydrogens, I'm just drawing the carbons. So this here, what I've got here, is just pentane. It's all single bonds. What I'm saying is that if you just put a bend in it, so I still have just 5, let's say I do this, okay, that's still just 5 carbons. That is the same molecule. To make an isomer, I have to have a different shape. So what you have to do is you have to go, okay, that's not going to count. That one there, that's rubbish. So I start with the 5 and I take one off the end and I put it somewhere else on the chain where it isn't just a bend. So not here, not at the end, but off the middle. So that is an isomer. Now that is the same as if I move it to the other middle carbon. Let's say I put it here. It looks a bit different, but they're the same. So this is not another one. The only other one there is where I put 3 and 2 off the middle one like that. So those are the 3 isomers of pentane. Now, pentane is the top one. This one here, the longest continuous carbon chain is 4. And so this is going to be based on butane. So this one here is called 2-methyl butane. And the third one, the longest chain is 3, and there are 2 of the single carbons. So it's called dimethyl. That means 2 methyls. propane. And we normally say they're on the second carbon. Sometimes you write 2,2, sometimes just 2 dimethylpropane. So those there are the isomers of pentane. Now, if I'm just going to stop sharing just for a minute. Oh, annotate, hang on. Let me just see if I can get rid of these. Oh, that's not very good. Okay, stop sharing. So that's isomerism of alkanes. If you're doing isomerism of alkanols, then you can move the OH around. So if you have 3 carbons, you can have the OH on the end or in the middle. Those are isomers as well. Hello, Silver Spring, you've turned sideways, or some of you have. Oh, that's better. Good. Okay, so let me just go back to share screen if I can. Oh, come on. So in alkanols, if you want to do isomerism of something like this, whoops, hello, what's happening there? If I want to do a nice, oh, hello, come on. If I want to do isomerism of something like this, then I could have my 5 carbons, 2 different isomers, just by moving the OH. So if the OH is on the end, or on the second one, or on the third one, these are all isomers as well. This first one is called pentan 1-ol, pentan 2-ol, pentan 3-ol. Okay, so there's the molecules. Now we normally run what we call a synthetic route. That is for making new chemicals. Okay, so we're talking about making some new chemicals, one into another. So that's what I'm going to do here. These are the sort of questions, you can't probably see this, but not very well, but this is a typical question from paper 2 in KCSE. And these are really quite difficult. Don't worry if you can't see it properly. We will come back to what that looks like. So what I do is I try to train people to understand or to learn this. This might be worth either taking a photograph of or drawing out. And where it starts is with alkenes over here, alkanols, alkanoic acids, and then up here, alkanes, and we'll go through the rest of it. So I'm going to go through the whole thing. Let's start with glucose being made into an alkanol. So if you're going to draw this, it's going to get bigger and bigger, but it's going to look like that. So if you leave space for it, then that will be helpful. So if you're going to draw it, start with the alkanol in the middle of the piece of paper. Okay, alkanol in the middle of the piece of paper. So we can take glucose and we can turn it into ethanol, an alkanol. Okay. So just write alkanol in the middle and glucose up there. And then to the right, write alkanoic acid. Okay, so alkanol here, alkanoic acid there. These are worth writing and learning. If you take an alkanol and an alkanoic acid, you may know that you make an ester. Don't worry about these at the moment. Just write alkanol and alkanoic acid. Okay? If you take these two, you can join them to make an ester. An ester is a chemical which has a very sweet, a nice smell. Okay, esters have a nice smell. Now let's go left. So from the alkanol, we can make an alkene. So an alkanol to an alkene, and it can be made back as well. So I can make an alkanol into an alkene and an alkene into an alkanol. So if you're drawing this, go back, alkanol here, one arrow from glucose down to the alkanol, and then one arrow from the alkanol to the alkanoic acid, two arrows, one from alkanol, one from alkanoic acid to ester, and then two arrows, one in each direction from alkanol to alkene. From an alkene, we can make an alkane, and we can also make an alkane into an alkene. We can also make an alkene into a polymer, which we're going to meet in just a minute. So that's the basic pattern. There are also three others. What we call an alkoxide, don't worry about that. And the salt, don't worry about that. And soap, don't worry about that. So let's just look at this. Let's just concentrate on this. So if you're writing this down, we're going to look at what happens between one and another, because quite often they ask what chemicals are necessary to turn, for instance, an alkanol into an alkanoic acid. So that's what we're going to do. And we sometimes talk about reagents, which are the chemicals we add, and conditions, which is what do we have to do? Do we have to heat it up? Do we have to add a catalyst? And so on. So we're going to start with glucose, and now on the arrows, we're going to say what is happening. We're going to start with glucose, and going from glucose down to alkanol. This is just fermentation. So this uses yeast and water and warmth, and that's it. From glucose to an alkanol is just yeast and water and warmth. From an alkanol to an alkanoic acid, it is oxidation. This here, K2Cr2O7, you may know, that is potassium dichromate 6, or orange potassium dichromate. It is a powerful oxidizing agent, and we have to heat it. So from an alkanol to an alkanoic acid, we use an oxidizing agent. An oxidizing agent. And it's very important that you know that one. From an alkanol and an alkanoic acid together, you make an ester. And to do that, we need just a little bit of some concentrated sulfuric acid. Concentrated sulfuric acid is a catalyst in this one. Now, I know this seems like a lot of detail, but what we are doing here is we are giving you how to turn one chemical into another. This would normally take a lot of lessons, but I'm giving you it because if you can learn this, you will be able to answer many, many questions. So let's go from alkanol now. Here's alkanol. There, I hope you can see it in the middle in the blue. From an alkanol to an alkene. Well, in this case, we need to dehydrate it. We have to take water out of it. And to do that, we use concentrated sulfuric acid and 170 degrees. Now, you might say, I will never remember concentrated sulfuric acid and 170 degrees. I think you can. I think if you concentrate, you can. In the opposite direction, from an alkene to an alkanol, this is a big industrial process. They do this in Kenya, they do it in UK, and they add water and they have to heat it and put it under pressure. So it's 300 degrees Celsius and 70 atmospheres. But the most important thing is from alkanol to alkene, it is dehydration. And from alkene to alkanol, it is hydration, adding water. From an alkene to an alkane, it is hydrogen and a nickel catalyst. A nickel catalyst. Okay? In the opposite direction, from an alkane to an alkene, that's cracking. And in cracking, it's normally 700 degrees and a catalyst. Okay, now that's a lot. So let's go through it again. So let's start again. So if I take some glucose, I can add some yeast and some water and warm it, and I will make an alkanol. If I take the alkanol and I heat it with some dichromate, an oxidizing agent, I can make an alkanoic acid. If I take some alkanoic acid and some alkanol with a little bit of concentrated sulfuric, I can make an ester. If I take an alkanol and I take the water away, I can make it into an alkene. If I add the water again, I can make the alkene into an alkanol. If I want to take an alkene and turn it into an alkane, I can add hydrogen and a nickel catalyst, and it will turn it into an alkane. So this is the basic pattern of it. This is the idea. If you can just learn this, and the best way is to cover these up and ask yourself, how do I make an alkanol into an alkanoic acid? How do I make an alkene into an alkanoic acid in 2 steps? What do I need to turn glucose into an alkanol, etc.? All right. Now, when you've got this is the pattern. If you write it out like this, you can test yourself a lot. You can work out, you can help, you can say with a friend, you could have this, and you could say, okay, I'm going to test you. How do I turn an alkanol into an alkanoic acid? How do I turn glucose into an alkene? There is no arrow from glucose to alkene, but there is from glucose to alkanol and alkanol to alkene. So you can do it in 2 steps. Glucose, yeast, water, warm, alkanol, turn the alkanol, lose water to turn it into an alkene. So that's the idea of this, okay? That's the idea of this as a pattern. Cover it up, have a look at the map. Can you do number 8? Can you do number 6? Can you do number 3? Just use it to test yourselves, but you have to learn first. Okay. You have to know about how to test for different chemicals. Quite often you will see, how would you test to show the difference between CH3, CH2, CH3 and CH3, CH, CH2? Here they are. How do you tell the difference between an alkane and an alkene? How do you tell the difference between an alkane and an alkene? Somebody tell me. Somebody tell me. How do you tell the difference between, so I've got 2 tubes, one with alkane, one with alkene. How do I tell the difference? What chemical can I add and what can I see to tell the difference? Somebody tell me. How do I tell the difference between an alkane or an alkene? Anybody? Alkene, alkane? Go for it, Silver Spring. Alkane, alkene. How do I tell the difference? Because you might have this in paper 3. You might have it in paper 2. How do we tell the difference between alkane and alkene? I mean, chemically, what test do I do and what is the result? Anybody? Come on, Sir Marys, you are clever. Come on, Osharika. Come on, Wamawini. Stand up for the men, Wamawini. Come on, Silver Spring. Let's have somebody with an answer. How do I tell the difference between, let's say, propane and propene? How do I tell the difference? Anybody? No? Come on. No? Okay. Okay. Well, you know, we're trying to... Oh, hello. Go on, Silver Spring. Let's have a look. Ah, you're absolutely right. Yes. No. Yeah. Really good point. Silver Spring said alkanes have single bonds, alkenes have double bonds. Yes. But if it asks for a chemical test, it means what chemical could you add which would change color with one of them, but not with the other? And the answer is two different tests. The first one is that if you try and set fire to them, alkenes produce more soot, more dark flame, but the best one is bromine water. And bromine water is orange, and orange bromine water goes colorless with an alkene, but stays orange with alkane. So bromine water, that is just bromine dissolved in water. You have 2 tubes, one propane, one propene. Add a little bit of bromine water, and the propene would go colorless. That's really important, really simple, very, very easy to remember. Bromine water goes colorless. Next question. So that's for alkane, alkene, and alkynes do the same. Alkynes also turn orange bromine water colorless. Next one. How do I tell the difference between an alkanol and an alkanoic acid? How do I know the difference between an alkanol and an alkanoic acid? Well, firstly, there is a hint in the name acid. Now, acids will do things which alkanols will not. So, for instance, an alkanoic acid will react with a carbonate to produce carbon dioxide. But the answer they like most is oxidizing agent. Oxidizing agent. If you add an oxidizing agent, an alkanol can be oxidized, and alkanoic acid cannot. So if I start with orange potassium dichromate and I add it to the 2 chemicals, hang on, Wamwini, I'll just come to you in just a moment. Let me just have a look. Hang on. Very good. Very good. Well done, Wamwini. That's great. Really good note. Well done. So potassium dichromate, acidified potassium dichromate, goes orange to green, or potassium manganate, potassium permanganate, you sometimes call it, goes from purple to colorless. You have to warm them. You have to warm them up. So you would have 2 test tubes. one with alcohol, one with alkanoic acid, and you would add orange potassium dichromate to both of them and warm them, and whichever went green, that shows the potassium dichromate has been reduced. Well done, Wamoini, has been reduced, and that means the alcohol has been oxidized. Okay. Oh, sorry, last thing. The test for an ester is that esters just have a very nice smell. They have a sweet smell, esters. So although you won't be asked how you test for them, in a question they may say the chemical X has a nice smell, in which case you can say, okay, that is an ester. Good. Okay, let's move on. We're not going to do that just now. I'm going to do something on polymers. So I'm going to do something on polymers. I'm going to do it on this I'm just going to do it on this because I want you to be able to see it, and I think sometimes you didn't, people couldn't see the whiteboard behind me. So let's get a pen. Okay, and I'm going to start with an alkene, and this one is ethene. Sorry about my handwriting, but it's not a very good board that I'm writing on. So this is alkene. Now, what an alkene can do, which is pretty clever, is alkenes can join together simply by opening up the double bond. And quite often they ask you what were to draw a section of a polymer. And this is what we call an addition polymer. So here I have 3 ethenes. Okay, they are just ethene molecules. Okay, I hope you can see that. Can everybody see that okay? Busharika, can you see that okay? Excellent. Okay. We are not able to see, please. Wamoini. Oh dear. Why not? Let me just try it again a bit further down. Okay. So I'll draw it a little bit further down, see if it is easier to see. I hope you can see this now. So I'm drawing some ethene molecules. Here's one, here's another, and I'm going to show you what happens when they join together. Now, you probably know this, but I just want to make sure that it makes sense. So all that is happening is that the double bond on each next alkene breaks. So this one here goes in between here, this one here goes in between here, and so on. So this then links together, and if you're going to draw it directly underneath, and it will make it easier. So I'm going to put those 2 carbons there, these 2 carbons here, these 2 carbons here, and hopefully this is making sense. Here are the 2 hydrogens on this one. Here are the 2 hydrogens on this one. There is now only a single bond here, and the other bond has gone to between this and the next one. So here is what the polymer, whoops, sorry. Ooh, no, hang on. Hang on. So this is what it looks. Oh, come on. So this is what it looks like. Each carbon has 2 hydrogens on and is joined to the next one. So it's just a long string of hydrogens, carbons with 2 hydrogens like that. I know it's not very clean, I'm sorry. Now, that means that we can write this as if I have n C2H4s, then that becomes C2H4N, because they are just joined together. However many I start with, this might be, let's say, 100,000. If you have 100,000 to start with of individual ethenes, then we get this at the end, which is the polyethene. So this is called ethene. In Kenya, you were very sensible and you stopped people having plastic bags, and polyethene is not so much of a problem anymore. Now, what you've got to realize is that this is an addition polymerization. Okay, this is called addition because only one molecule is formed. Whoops, sorry about my hand. Oh, lordy. Come on. This is a difficult board to write on, I'm sorry. Okay, this is called addition polymerization because all of the molecules just join together and only form one product. You are sometimes asked, what is a polymer? A polymer is just a very big molecule, made from smaller molecules. Now, the individual molecules are called monomers. So over here, these are the monomers. Monomers turn into polymers. Okay, single, mono, poly, many. So that's how we do it. Now, what is important about this is that every single addition polymerization works the same. Okay, it all works the same. Let me give you an example. This is making polythene from ethene. So I'm just going to change this. Let's say I'm going to put something. Let's put a red lump. Instead of this hydrogen here, I'm going to do that. I'm going to do it to this one, and I'm going to do it to that one. On the polymer afterwards, this one, and this one, and this one are like that now. Now, that doesn't look like that makes a lot of difference, but you have a hand up, Wamwini. I will answer you in just one moment. If instead of that just being like a pink hydrogen, if instead of that, I said, okay, let's get rid of that, get rid of that, get rid of that, and make them into methyl. So CH3, 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 then what we would have down here is CH3, CH3, CH3. In other words, I've changed this monomer, but the pattern is, yes, you can. If you want to record it, that's absolutely fine. Yeah, if you want to record it, that's totally fine. But I will send you the recording afterwards. So what I've done here is I've now changed the monomer. Now, what I've done, if you look at this, if I highlight it, I now have, instead of a 2-carbon chain, I now have a 3-carbon chain. So it's not ethene anymore, it's now propene. In other words, just by changing the type of monomer, I changed the polymer. So this now is, instead of ethene, it is, whoops, sorry, I haven't got rid of enough. Instead of ethene, this is now propene, which is 3H6, and now this would be polypropene. Okay, polypropene. So let's just have a look at that again. So let's just get rid of absolutely everything. Okay, let's get rid of everything. I'm going to show you how simple it becomes when I just clean it all up, get rid of all of it. I'll make it easier. At least I hope I will make it easier. So every time you draw out one of these, you draw it out with the double bond in the middle and the two groups attached to each of the carbons as above and below the alkene. Let me show you. So here we go, nearly there. Okay, so let's say I start with something which is really quite simple, like ethene. Then the product will be like this. And this will be joined to other ones either side. So we can simplify it by saying if I've got n of those, I will end up with something, and I'm just looking. Oh, don't do that. Come on. Come on. Oh, why is that not working? Okay. Oh, now the eraser stops working. My apologies. So I'll do it over here. Oh, the whole pen has stopped working. That's excellent. Come on. Why is this not working? Oh, I'm just going to come off this board. Huh. I'm just going to start another board. Sorry. Start another board. Okay, here we go again. Sorry. So I take the alkene, which always is drawn simply like this. Whatever those are on those sticks, it turns into a long chain like this. We can say it is a certain number of those joined together, having started with a number of those. So if I start with something like propene, which is CH3, CH double bond, CH2, I start by drawing this out as the C double bond C there, and then 4 bonds like that. I look at this carbon, it has 2 hydrogens. I look at this one, it has 1 hydrogen and 1 CH3. Now that means that this will then become, just like this, instead of it being hydrogen, 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 like that, it will now be a methyl there, a CH3 and hydrogen, and hydrogen, and hydrogen, like that. If I want to make polystyrene, polystyrene is this. Two hydrogens, another hydrogen, and what we call a benzene ring, which is normally shown just like this. And all that would happen is that this will change into single bond, 2 hydrogens up here, 1 hydrogen here, and the benzene ring. So all you have to do is keep on repeating it, okay? So this would look like this. Here's another 2, and another 2. Each of the ones on the top have got hydrogens on, and each second one, so this one has got a benzene ring on, that one's got a hydrogen. This one has got a benzene ring on, that one's got a hydrogen. That is how the polymerization works. Now, the clever thing about this is that if they show you a bit of the polymer, you can work out what the monomer was. Let me show you. Let's say in this one here that I've just done down the bottom, let's get rid of the monomer. Just for a minute, we'll get rid of the monomer. I can work out what the monomer was by just realizing that it must have been a 2-carbon unit. So I find 1 carbon, another carbon, and that here is basically the monomer. So the monomer is C, it had a double bond in, and now I just copy this out. So it is 2 hydrogens, 1 hydrogen here, and this funny squiggly thing, hexagon, not well drawn, that's it. So you can go from the polymer to the monomer, or the monomer to the polymer, and so on. Good song, Oshirika. Very good. Okay. So that's quite difficult, but that is what polymerization is about. Okay, that's what polymerization is about. The only other one that we have, the only other bit which is relatively complicated, is detergents and soaps. Detergents and soaps, and I just have time to do detergent and soap, so I will do that now. So I don't know if you know how soaps are made and detergents, but they are very different. And the basic plan is that a soap is made from an oil or a fat and some sodium hydroxide, and a detergent uses an acid to react with an organic molecule. And an organic molecule can be almost any organic molecule, but to make a soap, we start just with an oil or a fat and we heat it with sodium hydroxide. And by heating it with sodium hydroxide, we do a process called saponification. You don't need to know the word, but that's how you make a soap. Now, most of the questions do not ask you about can you make a soap and so on. They just ask you whether you can recognize it. So we're not going to do how we make it. We're going to just recognize them. So here we go. So a soap looks like this. It is a long chain of carbons and hydrogens, and at the end, it has a carboxylic acid, alkanoic acid group and a sodium salt. This is a soap. A detergent, the sort of thing we normally wash clothes in, is again a long chain, but at this time it is an OSO3 minus Na plus. Okay, so soap has this bit, and a detergent has this bit. And if they ask you to draw it, that's what they're asking for. So soap has this, detergent has this. The funny thing is, soap does not have the S in it. So the soap is COONA, and detergent is OSO3 minus Na. Okay? And the only thing they ever ask you about is what happens with water containing magnesium. So Mg2 plus AQ or Ca, it's the same, it does exactly the same. And this one forms a scum. A scum is not good. This one forms no scum. So in other words, if you get soap and you have water containing magnesium ions and you try and use soap, you get a white fluffy substance on the water, and it is not attractive and it makes marks on your clothes. If you use a detergent, that's fine. There is no scum. But, and there is a problem. And the problem with detergents is these do not break down easily. So if you see a river and a river has many, many bubbles on the top of it, that will kill the fish. And that is almost always the detergent which is doing it. Okay, detergents make many, many bubbles on the river and they do not break down easily. They are very, very difficult to get rid of. Okay. So soap makes scum with your clothes, not good for washing clothes in. Detergent much better, but detergents do not break down easily, but soaps do break down easily. Okay, that's quite important, just recognizing this here. All right, that is a lot. That is a lot of information I've given you. I'm sorry it's too much, really, but what I'm going to do is I'm going to send your teachers some questions. And the questions have answers with them, and your teachers can print them out. They are all from KCSE. I will just show you some of them now so you can ask your teachers for them. So there are questions which I have set, and you can have them as questions and you can have them with answers. So there are ones on polymers. There are ones about how to calculate how big the monomer and the polymer was. There are other ones about other kinds of polymers, which are a bit, this question is only for people who are going for top marks. This is about detergents and soaps. Okay, so that's all about detergents and soaps. This is about vulcanization of rubber. Rubber is very soft and springy, but if you heat it with sulfur, it becomes much harder. If you made your car tire out of normal rubber, it would break really easily. So it has to be heated with sulfur, which forms cross links, which makes it very strong, and so on. So that's one set of questions. There is another set of questions. They're simple questions. There's another set of questions. There are ones about tests that can be carried out on molecules. Oh, why is that not showing? Why is that not showing? Ooh, that's gone a bit messy, but anyway. There are ones about how you test between different substances. So there are ones like that. Oh, this is all moved, that's why. There are all sorts of reactions. You will get these, you will get all of these. And then There are a set of questions which I have found, which are all from the last 3 years organic questions. So you will get all of those. Now it's about time to finish. I'm sorry this has been a lot of information, but some of you will remember some of it, which is good. What I would like to know is what subjects you would like to do in the next 2 weeks before the examinations start. What would you like to do? Anybody tell me what you would like to do in the next 2 weeks? We will do just questions. Okay, we will look through questions. So what topics would you like to do from Form 3, Form 4? We're not going to do questions from Form 1, 2. There are too few marks in Form 1 and 2. So we want to do either 3 or 4. So do you have a topic you would like to study next week or the week after? Anybody? Write it down, show me, or unmute and tell me, please. I will probably do one lesson on practical on paper 3 and what you might need to do. Show me St. Mary's. Show me Osharika. Radioactivity, Osharika. Radioactivity graphs, okay. St. Mary's, a little bit closer, please. Sorry, show me again. Show me again, St. Mary's. Let me just see, because your camera is quite small. Something and its atoms. Electrochemistry and radioactivity, Wamuini, okay. I'm sorry, St. Mary's, could you write that a little bit with a bit stronger, please? Because you're, try it again. Show me again, please. St. Mary's, show me again. Come closer. Closer, 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 closer. Carbon and its atoms. Ah, okay, okay. Carbon and its atoms. We will try to do something on that. Okay. Radioactivity, yes. Electrochemistry, okay. Carbon, we will try and do something, but we will also do paper 3. How many of you have done a lot of practical work and only a little practical work and basically no practical work? Have you done a lot of practical work? Excellent. Wamwini. A little or no practical work? Silver Spring. Lots. Excellent. St. Mary's. Lots of practical work. Little bit. Usharika. Great. Usharika. Okay. All right. Okay, that's good. Thank you very much for being patient. I know the organic is difficult. If you can learn that map, glucose, alkanol, alkanoic acid, alkene, alkane. If you can learn those. Sorry, Osharika.
No question.
No questions.
No.
Good.
No question.
There is a question from Wamuini.
Yes, Wamuini. It stands for chlorofluorocarbon. Chlorofluorocarbon. It's normally, for instance, 1 carbon with 3 chlorines and 1 fluorine on it. So it's CCl3F. Okay, just C, 1 carbon, 1, 2, 3, 4 bonds, 3 chlorines, 1 fluorine. Those are the chemicals which used to be used in refrigeration. Not anymore, but they still cause problems in the upper atmosphere. Chlorofluorocarbon. Any other questions, anybody? I'm going to stop recording.